Hello, welcome back to our third part of Chapter 10's lecture. In this part of the lecture, we will be looking at sound waves. Let's start with the definition of sound. A sound wave is vibrations consisting of compressions and rarefactions traveling through air, water, or solids. Sound waves are produced by vibrating objects. For example, a tuning fork is a piece of metal here, and if we strike it with a hammer, it vibrates back and forth. What happens is as it vibrates back and forth, it compresses the air molecules next to it every time it moves to the right, and it creates a region of higher pressure, which is called a compression. When the tuning fork moves to the left, it leaves a region where there are less air molecules and lower pressure, and this is called a rarefaction. And these compressions and rarefactions travel away from the tuning fork at the speed of sound. We'll see an animation of this on the next slide that will help clarify what's going on here. One way we can plot this is a plot of pressure versus position. And so in these compression regions here, we see the pressure is high. So that's these peaks here on our graph. And then in between the compressions are the rarefactions where the pressure is lower, and those are represented by the troughs in the graph. So this graph here looks very much like the graph that we saw in part 1 of the video when we looked at, for example, waves on a string. So mathematically it has a very similar form and properties in terms of the wave. The speed of sound, so how fast do these compressions and rarefactions move? Well, this is called the speed of sound. So in air at room temperature and sea level, the speed of sound is about 340 meters per second. In water, since the water molecules are closer together than they are in air, the sound can transfer from molecule to molecule much more quickly. Therefore, the speed of sound in water is much higher. It's about 1,500 meters per second. And if we go to a solid like steel, again, the steel or iron atoms are very closely packed and they're held together by strong bonds. So any vibrations in those atoms can be transferred to their neighbors very, very quickly, resulting in a much, much higher speed of sound, and we see it's somewhere around the order of 5,000 meters per second. So this is a nice animation that shows how sound waves are produced and how they travel. And this is kind of fascinating here. What this is showing is we've got a tube or a pipe just filled with air molecules. All these little black dots represent individual air molecules. Over here is a plunger or a piston that is moving back and forth, creating some frequency of sound. And you can see whenever it moves to the right, it pushes the molecules towards each other and makes a compression. One of these regions where you see it darker, where there are more air molecules closely spaced together. When the piston moves back to the left, like right now, you can see it leaves a rarefaction, a region where there's more space and less pressure between the air molecules. Now, one thing we notice here is that these compressions are moving to the right, and they're moving at the speed of sound. This is in slow motion, of course. But remember that the individual molecules are not moving from one end of this pipe to another. In fact, if you look at these red tracer molecules, there's one here, here, and over here. If you watch what happens to them, they simply move back and forth, left to right. They stay in the same place in general. They just move back and forth as the wave passes through them. So sound waves, just like any wave, it passes through the air. It doesn't carry air with it. Now, this is a longitudinal wave because the air molecules are vibrating back and forth in the same direction that the wave is traveling, which is horizontal in this picture here. Down here is a plot of sound pressure, and you can see that these regions of high pressure here, the compressions, are represented by the peaks here. And so we see the peaks and the troughs moving to the right. We can define the wavelength of sound as the distance between two adjacent peaks. In order to better understand how sound is produced, let's take a look at how a loudspeaker works. So speakers are found in radios, stereos, TVs. Your cell phone has a speaker in it, obviously when you press the speaker button, or when you hold it up to your ear, there's a tiny speaker in there as well, and as well as headphones, earbuds, speakers are found, in anything pretty much that produces sound. So the way it works is actually quite simple. There is what's called a speaker cone here, which is either made of paper or plastic, and it is attached to a coil of wire that leads to the source of the sound, which is some electrical signal. There's also a magnet inside the speaker here, and what happens is, and this is something we'll learn about later, in the course if you study electricity and magnetism, is when electric current flows through the wires here, it creates a magnetic field, and that either is attracted or repelled to this magnet here. So if the sound signal here is varying at, let's say, 400 hertz, 400 cycles per second, what happens is this speaker cone is going to move back and forth at 400 cycles per second, 400 times per second, and it's going to produce a sound wave with that same frequency, because remember, as it moves back and forth, it's going to compress the air molecules in front of it 400 times a second. Here you can see in this animation, the speaker is actually moving back and forth, with some signal that's fed into the coil here. So what we're going to do shortly here is we will listen to some different frequencies and see how our ears and our brain interpret that sound. So this has to do with what we call pitch, and pitch is basically a musical term that determines how high or low a sound is on the musical scale, and pitch is all about the frequency of the sound. So let's start here by listening to sounds at different frequencies in a video simulation demonstration. This is an online tone generator that creates a musical tone or pitch where we can control the frequency, which is shown right here. So I'm going to start here at a frequency of 200 hertz, and let me turn up the volume here so you can hear this. So what's happening at this frequency is the speaker inside the computer, and also the speaker inside the device that you're listening to right now, is vibrating back and forth 200 times per second to produce this pitch. Now watch what happens as I reduce the frequency. So now we've gotten to such a low frequency that we basically don't hear it anymore. It's just vibrations once we get down here below about 20 hertz. But let's go up now and listen to it as we increase the frequency to higher and higher frequencies. Turn down the volume a little bit because it starts to get really loud. The higher frequencies have a lot more energy than the lower frequencies. Here we're at about 750 hertz. This is 1000 hertz right here. There's 1000 hertz. And I can double it by hitting this button here. This goes up, that's called an octave in music. Let's go to 2000 hertz. 8,000 now. And I can keep going up now. Once we get above 10,000, interestingly, my hearing starts to fail, and I can't really hear the pitch, but you guys probably can still hear this at home. I'll turn up the volume a little bit for you. And depending on the speakers, you may or may not be able to hear this as I go to 11,000, 12,000, 15,000 hertz. And the upper end of human hearing is usually considered around here at 20,000 hertz. Now we can go back down. So that is the effect of different frequencies. It produces a different musical pitch. If you want to play around with this tone generator, you can see the URL right up here, and you can pull this up on your device and test your hearing and see what your ears hear at different frequencies. So you just got to hear the effect of different frequencies and how it makes different pitches that we hear with our ears. And it's interesting to see that the range of hearing depends quite a bit on the species of animal. For example, elephants with their larger ear structures can hear only lower frequency sounds up to about 12,000 hertz, and they can apparently hear subsonic sounds that we would not be able to hear. Our hearing goes from typically about 20 hertz to about 20,000 hertz for a young, healthy person. As you get older, we start to lose the upper part of the spectrum of sound. As I mentioned during the demonstration that we just heard, I can only hear sounds up to about 10,000 hertz because I'm a little bit older than you guys. I think even younger kids than you can hear the full range of sound here. But it's interesting to look at some of these other species. For example, dogs, as you probably have heard, they can hear sounds much higher in frequency and pitch than the human ear can. And so a dog whistle, for example, that are used by the police and the military is a ultrasonic sound that we can't hear, but it's a dog can plainly hear that sound. So the dog whistle is set to some frequency above 20,000 hertz where our ears go to. Look at the mouse. It can hear up to something like 90,000 hertz. I'm guessing that's due to its tiny little bones and structures inside of the tiny mouse's ear that allows it to vibrate faster. But notice that the lower end of the frequency for the mouse is around 1,000. That is a pretty high pitch to you and me, and apparently they can't hear anything lower than that. Bats have interesting hearing senses. We'll talk about their echolocation later, but you can see they also go to extremely high frequencies, as do porpoises. One of the fun things about watching most science fiction movies is the action scenes where there are battles in space and something is blown up, like a spaceship or the Death Star or whatever is blown up, and we hear this tremendous explosion, right? And makes it really exciting. However, that's all bogus, right? There is no sound in space because there is no air in space. Sound requires a medium to transfer through. So in the vacuum of outer space, if something explodes like this, it makes no sound at all. It would be completely silent. There's an interesting way to demonstrate this using what's called a bell jar. And inside this bell jar is actually a bell that will be ringing, and we can pump the air out of this bell jar and listen to the sound become more and more quiet. So I'll have you watch this video demonstration of another instructor that does this demonstration.
Hi, today we're talking to you about pressure and some different experiments we can do with pressure. Here at Rutherford Laboratories, we have received a new affordable bell jar and we will demonstrate a few things with it today. This bell jar sucks out the air from this container, the bell. And so what we will do is demonstrate how sound needs air particles to vibrate in order for you to hear it. This bell makes a sound like this. What we will do is place the bell jar, place the alarm bell in this position. Then we will turn it on. Place the bell jar on top of it. Notice you can still hear it. Now we will turn on the compressor. Oh, not compressor. Vacuum pump. We have a nice vacuum pump. Doesn't make too much noise. And we'll just wait, see what happens. Can you hear any difference? We'll let it run for a minute, and then we'll turn off the compressor so you can really see if there's any difference in the sound. Now I'll turn it off. Oh, I forgot to close the bell jar. Can you hear it getting louder again? Let's turn it on again. Now the important step on this little bell jar, it has a nice valve. So you just turn the valve and it keeps the air from going back in. So I will do that before I turn off the vacuum pump. Turn off the vacuum pump. Can you hear the bell? Let me give you a close-up look. Can you see it? Can you hear it? Now, watch what happens when I open the valve. Listen. Opening this valve right here. Letting the air in. Can you start to hear it? I do believe you can. It's a very neat property how air is required, some medium, to transfer sound. There are particles that need to be vibrated from the source all the way to your ear. That's it for this video. Check back for more. Signing off, Mr. John.
So the speed of sound that's how fast the sound wave moves through air. And the speed of sound depends on how fast the atoms or molecules in the medium can move and interact with each other. So if we have air at a cold temperature, so 0 degrees Celsius, remember, is the freezing point of water. So that would be on a cold winter day up in the mountains or something like that. And you can see that the speed of sound is pretty slow, relatively low on this chart. It's 331 meters per second. So the molecules in gases in general are far apart. So the speed of sound in any gas is going to be lower than it is in a liquid or solid. And also at lower temperatures, remember, the gas molecules are moving more slowly. Remember, higher temperatures means more thermal energy, more motion of those molecules. So if the molecules are moving more slowly, they will take a longer time to bump into their neighbor molecules. So as a result, the speed of sound is relatively low. You can see that air at room temperature is a little bit higher. It's 343 meters per second. This is due to the molecules moving faster at higher temperatures. Now, helium is interesting. Helium gas is very light. Of course, that's why they use it in helium balloons. And because of those lightweight molecules, they can move faster and react faster. They have less mass, less inertia. And so as a result, the speed of sound in helium is about 3 times higher than it is in air. And interestingly, this is why if you ever breathe helium out of a balloon, you can make your voice sound really high pitched. And the reason for this is the sound waves inside your vocal cords and voice box move 3 times faster, and that creates frequencies that are 3 times higher. And remember, higher frequency means higher pitch. So that's why you hear your squeaky chipmunk-like voice if you breathe and talk with helium. Oh, and by the way, it's not on this chart, but I've seen a demonstration where somebody breathes argon gas, and argon is a heavier gas than air. And also it's harmless because argon is one of the noble inert gases. Like helium, or it doesn't react with our body, so it's safe for short periods of time at least to breathe. So anyway, I've seen people take a breath or a whiff of argon gas, and it gives them a very low voice. They sound like Darth Vader. Even women or girls that have high voices can make their voice sound extremely low. All right, going down the chart here, we see liquids are next, and liquids have much higher speeds of sound. This is just because the molecules are closer together. They can interact with each other much more quickly. They don't have to move as far to bump into their neighbors. And then finally at the bottom are solids. And because solids are tightly packed atoms and molecules, they react very quickly when there are vibrations in a solid. So the speeds of sound are very fast. In solids. You can see some of these, and I put here's diamond down here, has the strongest bonds of any substance, and therefore it has a very, very high speed of sound, something like 12,000 meters per second. All waves reflect off of surfaces when they encounter a surface. And sound waves are included, and for sound waves we call this an echo. So an echo is a reflection of a sound wave off of a surface. So in this example here, here's the boy, and he claps his hands. So the sound wave travels distance d to this mountain here, and it bounces off, and then it comes back the same distance, d again, and he hears it sometime later. So suppose the boy hears his echo 4 seconds later. How far away is the mountain? So this is a way that we can use sound as a sort of an echolocation device to measure the distance to a faraway surface. So we know that velocity, or speed, is distance over time. So the distance that the sound wave travels is actually 2 times this distance, because it has to go there and it has to come back. So the total distance it travels is 2d, and the time is t. All right, so what we're going to do here is we want to know how far away is the mountain. We want to figure out what is d. So we're going to solve this for d. So we can multiply both sides by t and divide by 2, and we get distance is equal to vt over 2. Speed of sound, we can use 340 meters per second. The time was given as 4 seconds, and we have to divide that by 2, so that comes out to be 680 meters as the distance between the boy and the mountain. Echoes have lots of other applications that are, some of them are very important. For example, ultrasound is a non-invasive diagnostic technique where a medical technician can use an ultrasound transducer to send ultrasonic sound waves. I mean, we can't hear them. They're higher in frequency than our ears can hear, and it'll send them into our bodies, and they bounce off of different tissues and organs. In this case, it's a human fetus, and we can actually make an image on a computer screen to see the inside of our body. So that's a pretty cool technology. Sonar is used by boats and ships, and basically it sends sound waves down, and they bounce off the bottom of the ocean or the lake, and they come back, and the software allows the people in the boat to basically tell the depth of the water. And now more sophisticated sonar systems can actually map out the structure of the bottom of the ocean or lake, and you can see that on a screen. And for example, this is how the Titanic was discovered, something like 13,000 feet below the surface, by using sonar like this. Bats have an amazing sense that we don't have, and it's called echolocation. They send out sound waves. They're ultrasonic to us. We can't hear them. And they bounce off insects, and they come back, and the bat can interpret those echoes. And actually, I think, biologists believe the bat's brain is able to form almost an image from these sound waves, which is something, we can't even imagine what that would be like, to be able to see sound. But by doing this, they can hunt at night, and they can basically detect insects that would be invisible to any other animal in the dark. Some of the older cameras used autofocus based on ultrasound. They would send out a sound wave, it hits the subject of your photograph and comes back, and it measures the time distance there, and sends a signal to the lens to focus depending on this distance here. One of the most fascinating phenomena of sound is the so-called Doppler effect. The Doppler effect is a change in frequency due to the motion of the wave source or receiver. And I'll leave the explanation up to the video, but basically when you have a source of sound like a car, or let's say a fire truck with its siren going, the observer over here will hear a different pitch of sound as the observer over here. Because what's happening is, as the sound source here is moving towards this observer, the truck is basically chasing its own sound waves, and they tend to bunch up closer together, resulting in a higher frequency. On the other hand, conversely, for this observer over here, these sound waves are moving back towards him or her, and since the sound source is moving to the right, these sound waves are spreading out in space, and therefore as they arrive here, they are arriving at a lower frequency, so you hear a lower pitch. So this leads to a very fascinating effect called the Doppler effect. So let's go ahead and watch a couple of short video demos that will explain the Doppler effect.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense. But it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Related to the Doppler effect are shock waves and what are called sonic booms. So this is these are just some diagrams here showing that we have in the middle here we have an object that's producing sound. So that, again, this could be a whistle or a car with a horn going or whatever. And in this first picture here, the speed of the object is 0, so it's at rest. So the sound waves are coming out basically in circles, and these circles are expanding at the speed of sound in all directions. You can think of them like bubbles, right, of representing the sound waves. Now, if the object starts moving to the right, like in this picture, all right, what we've got now is the Doppler effect. We see the sound waves bunched up in front and spread out behind. And this holds as long as the speed of this object is less than the speed of sound. But as this object gets closer and closer to the speed of sound, it eventually reaches the speed of sound, which is called Mach 1. And what happens now is the object that's producing sound is traveling as fast as the sound is trying to leave the object. So the sound waves are all piled up on top of each other, and this is called the sound barrier. It's a region of high pressure due to all of these sound waves just stacking up on top of each other. And it was a technological challenge to build military aircraft that could reach and break the sound barrier. And it was finally done famously by test pilot Chuck Yeager in 1947 in the X-1 experimental aircraft. And it reached and exceeded a speed of 760 miles per hour and broke the sound barrier for the first time. Now, what happens if you keep going faster and faster past the speed of sound? For example, what if you go Mach 2 or Mach 3? That would be 2 or even 3 times as fast as the speed of sound. Well, what happens then is, since you're out running your own sound waves, you're sort of leaving your sound waves behind you, and there are these expanding bubbles. But along the wave front of these expanding bubbles, where they all sort of stack up, there is a what's called a shock wave. And again, this is a region of high pressure because of all these wave fronts piled up on top of each other. And this shock wave travels away from the object here at the speed of sound. But when those shock waves reach the ground, like let's assume this is an aircraft that's going at Mach 2, it's going to produce a shock wave which we call a sonic boom. When the shock wave hits the ground, it sounds like an explosion, and it carries enough energy that it can actually break windows in buildings. So for this reason, it is not allowed to have an aircraft travel at more than the speed of sound over populated areas. Here are some interesting pictures of shock waves. This is a rifle being fired. You can see the bullet out in front here, and there's the shock wave due to the bullet traveling, and then also from the high amount of pressure coming from the tip of the rifle here, we see this bubble of expanding air, basically. This is the shock wave, and this is the crack that we hear when a gun is fired. This is the loud sound that we hear. It's due to that shock wave. This is a close-up of a bullet going at Mach 1.5. So again, this means it's traveling at 1.5 times the speed of sound. And you can see that out due to the tip of the bullet here, it's creating this shock wave here, and there are other shock waves coming off the sides of the bullet. And also, you can see some turbulence, which is kind of interesting, in the air behind the bullet. You don't have to go super fast to create a shock wave. As long as you're traveling faster than the speed of the wave, you create a shock wave. So here's this little duck swimming in a pond, but the duck is swimming faster than the waves that it creates, because waves in water, of course, go very slow. So as a result, the duck leaves the shock wave, and this is called a wake, and we see this behind a boat as well. All right, and finally, this is an old picture from a nuclear bomb test, and you can see the shock wave. There's actually two here. This is from the blast, and you see another one going through the water. You can see some ships here. These are not manned ships. They're just empty ships that were used to test the power of this explosion. But this is the expanding shock wave that is traveling through the water here. Here's a couple more interesting examples of shock waves. As an aircraft breaks through the sound barrier, there's a shock wave, which is high pressure that's formed, but behind the shock wave is a region of low pressure, which causes sudden expansion of the air. And when the air expands, it cools. So this rapid cooling of the air causes condensation of water vapor in the air, and it forms a vapor cloud. So you can see this really interesting vapor cloud, and this is the actual shock wave. You can see that shape, that kind of conical shape coming off of the aircraft here. There's even a small one coming from the cockpit of the airplane here. But this is just a region of low pressure behind the shock wave where the air is expanding and expanding so quickly that it cools and condenses the water vapor in it, forming that cloud. Another really fascinating effect of sound is the effect called beats. Beats are a pulsating, throbbing sound heard when two slightly different frequencies are heard together. And we'll see a demo of this shortly, but let's look and see how this works. So imagine we have two sound sources. We'll call the first one wave 1, that's the blue one here, and so it has a frequency F1. And wave 2, the second sound source, we'll call it wave 2, and it has frequency F2. Now, looking at these, it's hard to tell, but it turns out that F1, the blue wave here, is slightly higher than F2. You can kind of see that these peaks are a little bit closer together. That means it's a slightly higher frequency. It really becomes obvious if we overlay these two. Now remember, what superposition is all about is basically taking the two waves and overlapping them and then adding their amplitudes together. So something interesting happens here when we overlap these two waves. When we combine them like that, notice what happens is that right here, the two waves, the pink and the blue, are in phase. So this is going to be constructive interference. This is going to produce a very loud sound. But over here, notice because they're not the same wavelength, as we move here, they start getting out of phase. And when we're right here, they're they're exactly out of phase. This is destructive interference, and so we expect to hear no sound. So the amplitude is basically small or zero. But then as we keep moving to the right, the waves start to catch up with each other again, in frequency, and now they're overlaid again, and they're in phase. So this is going to produce a loud sound. And then as we keep going to the right, we're out of phase, in phase, out of phase, and in phase. So what we actually hear is the combined amplitudes of this blue and this pink wave produces a loud sound, a soft sound, a loud sound, a soft sound, etc. And if you do the mathematics for this, which we're not going to do in this course, but it's not that difficult, the frequency of these beats, all right, this is loud, soft, loud, soft. So these beats that we hear are these throbbing sounds. The beat frequency is simply the difference between the two frequencies. It's the high frequency minus the low frequency. So let's go ahead and look at and listen to a demo of beats where we're going to use two speakers connected to two different sources, and we will intentionally change the frequency of one of the speakers just a little bit so we can hear the beats. So I'm here in my lab, and I have two speakers here from a stereo, and they're both connected to this device back here, which is called a signal generator. And the signal generator has two outputs. Each output is driving a different speaker, and I've got them both set to 600 hertz right now, 600 cycles per second. So that's the tone you're hearing. Now, since the two speakers are set to the exact same frequency, we don't hear any beats. It's a steady tone. So let me set one of the speakers to 601 hertz. So this is 601 and this is 600. So listen for the beats now. We're hearing a beat frequency of 1 hertz or 1 cycle per second. Remember, the formula for beat frequency is just the difference between the two frequencies gives us the beat frequency. So 601 minus 600 gives us 1 beat per second. Let's go to 602. Now we're hearing 2 beats per second. 602 here, 600 here. The difference is 2 beats per second. Let's go to 3. 3 beats per second. 604, 600, 4 beats per second, and so on. This is 605, 606, 607, 8, 9. So here we have 610 and 600. So we're actually hearing 10 beats per second, which if we listen carefully, you can hear it, but they're pretty fast. And I can keep going up from there. And now we can start to hear the difference in tone between the two speakers. They sound really out of tune now, and the beats are so fast now, this would be about 25 beats per second. We don't hear them anymore. So let's go back down. All right, so what I'm going to do now is I'm going to go to 600.1 and 600. So the difference is only 0.1. Let me go here now. The difference now is 0.1 hertz, which is 1/10 of a beat per second. What that means is it takes 10 seconds for the full beat frequency. Soft, loud, all right, 5 seconds later, soft again, and then loud. So every 5 seconds it changes from soft to loud, with 10 seconds for a total beat period, and 1/10 of a hertz for our beat frequency. Before we talk about our next subject, just in regards to the beat frequency demo we just heard, this is very practical for musicians. They can basically tell if their instrument is in tune or out of tune. Our ear is usually not sensitive enough to listen or to detect 1 or 2 hertz of different pitch. But if we have an instrument, let's say 2 instruments are going to play together, duet in a concert, they both play the same note. If they are perfectly in tune, there'll be no beats heard. But if one instrument is just a little sharp or a little flat, that means the pitch is just a slightly bit higher or lower, then beats will be heard. And we heard in the demo, the video, they're very easy to detect, and the musicians know that they're not in tune, and they can tune their instruments. Okay, let's move on to our next topic, which is standing waves. This is another very important and practical application of studying waves, and there's some very interesting phenomena that we're going to look at as well. So let's start by watching a video demo from another instructor that I think you'll find entertaining.
Today's demonstrations will involve a string fixed at both ends. The left end is attached to an oscillator which will be oscillating up and down in simple harmonic motion at a known frequency. And the right end is at a constant tension which is caused by a constant hanging mass. Okay, let's turn it on and see what happens. That is a standing wave pattern.
Cool.
Yay.
I don't get it. The string is just going up and down.
Okay, let's watch what happens when I change the oscillator to 30 Hertz. And let's add a top view which is zoomed in to show the oscillator and the left half of the string. Remember, the oscillator is now moving up and down 30 times every second.
Why isn't anything moving?
That is a
Good question.
yeah.
Wait a second. Look at the hanging mass in the lower right-hand corner. It's moving like this is a normal video.
What?
The frame rate of this video is 30 frames per second.
Oh, so we are looking at 30 pictures of the demonstration every second, and the oscillator is going up and down 30 times every second.
That means the oscillator and string return back to the same location 30 times a second, and then the video camera takes a picture of it.
That looks weird.
Which is why every video I show of the demonstrations from here on out will be 32 times slower than real speed. And now you can see what is actually happening in the standing wave pattern. Let's now put 3 different frequencies on the screen at the same time to better see the differences between the 3 standing wave patterns.
I still don't really get it. The string is just going up and down in all those examples.
Okay, well, how about this? I will use some video editing trickery to add an echo of each wave pattern so you can better see the 3 standing wave patterns being created.
Whoa. There are like different humps.
Yeah, 1, 2, and 3 humps depending on the frequency.
Right, but the string is still just going up and down. It's just there is a pattern showing how they go up and down.
Dare I say a standing wave pattern?
Absolutely, Billy. These are the standing wave patterns. However, I want to remind you of what is going on here, which I can demonstrate by plucking the string. The wave pulses created by the oscillator are sent down the string, reflected and inverted, and then sent back down the string. The wave pulses going back and forth constructively and destructively interfere with one another and set up the standing wave patterns. You just do not see the wave pulses which are going back and forth. All you see is the resulting standing wave pattern, which is why I have created this animation to show you the wave patterns which constructively and destructively interfere to create the standing wave patterns.
That's cool.
What is that?
I don't know.
Actually, let's look at the individual parts of the animation. The blue periodic wave is moving to the right and represents the periodic wave which is being generated by the wave oscillator. The red wave is moving to the left and represents the periodic wave which is the result of the blue wave being reflected and inverted by the fixed end on the right. But the truth is that neither of those waves exists by themselves. What we actually see is the constructive and destructive interference of those 2 waves creating the black standing wave pattern. Now, let's pause the animation to discuss what happens at specific points. With the waves paused here, Billy, tell me what you see.
At this point, the red and blue waves have the same amplitude, but are mirror images of one another.
Then we get total destructive interference.
Right. The red and blue waves completely cancel one another out, and the result is just a flat string.
Absolutely. At this point, there is total destructive interference of all waves, and the net result is no wave at all. And Bobby, what do you see when we pause the animation here?
Well, the red wave is in the same location as the blue wave, right?
Correct.
Then the two waves constructively interfere with one another and create the same wave shape as the red and blue waves, only with twice the amplitude, right?
That is correct, Bobby. At this moment, both waves constructively interfere with one another and create the standing wave with twice the amplitude. And pattern. On this standing wave pattern, there are 7 locations of total destructive interference. Those are called nodes. There are also 6 locations between the nodes called antinodes, where the waves create a larger amplitude wave via constructive interference.
Nodes are locations of total destructive interference where the standing wave is always at equilibrium.
And antinodes are locations where there is a large amplitude due to constructive interference.
Got it.
You both just stole my thunder.
Yeah.
Okay, let's switch back to the real demonstration rather than the animation and identify the locations of the nodes and antinodes. Also, I have added 61 and 76 hertz as well to show a total of 5 standing wave patterns.
I do not really see the standing wave pattern.
Where are
I
they?
think I can see them.
Oh, right, sorry. I'll add my video echo of each wave to make it easier to see the nodes and antinodes. Is it easier to see them now?
Sure. 15 hertz has 2 nodes, one on each end and one antinode in the middle.
30 hertz has 3 nodes, one on each end and one in the middle, and 2 antinodes, one between each pair of nodes.
45 hertz has 4 nodes, again, one on each end, and then 2 more nodes, which split the string into 3 parts, where at the center of each part is an antinode.
I think I'm sensing a pattern here. Starting at 15 hertz with 1 antinode and 2 nodes, we add 1 antinode and 1 node for every 15 hertz we add to the frequency.
Yes, it's pretty close to that. In summary, standing wave patterns are waves generated in a medium which interfere with the waves which are reflected to create a pattern of waves which appear to stand in place.
That's why they are called standing waves. Duh.
Nodes are locations where the wave interferences cause total destructive interference. Antinodes are locations where the wave interferences cause constructive interference. And standing wave patterns are only possible at specific wavelengths, which create, in the case of nodes on either end of the medium, integer multiples of half wavelengths of the wave. Thank you very much for learning with me today. I enjoyed learning with you.
So as we saw in the video demo, standing waves are produced when the waves are allowed to bounce back and forth between boundaries. So for example, if we have a string tied between 2 posts here, these waves are going to bounce back and forth and they're going to interfere with each other. And we saw something like this in the video that you just watched. The yellow wave here is going to the right. It's hard to tell what color that is. It looks like it's light blue, is moving to the left, but what we actually see is the purple wave, and that's the superposition or the addition of those other 2 waves. And notice the purple wave, it just bounces up and down. It doesn't travel left or right, and so this is the phenomena of a standing wave. What we also saw in the video is that, these standing waves, they set up a pattern of fixed nodes and antinodes. And so this is a self-interference phenomenon. So with a string, this is the first mode of vibration. There's basically one hump here. This is also called the fundamental frequency. The second allowed mode of vibration, which is sometimes called the second harmonic, is there's 2 humps basically here, and this is showing what it's actually doing over here, how it's vibrating up and down. And then the third mode would have 3 humps, and you remember that the humps are called antinodes, and then the places where the string is basically not moving, which are the two ends, and then also these minimum positions here are called nodes. There are some interesting examples of standing waves other than waves on a string. For example, a laser pointer or an industrial laser has a laser cavity with light bouncing back and forth between mirrors, basically, on the ends of this cavity. And when the light is bouncing back and forth extremely fast, right, it's traveling at close to the speed of light here, and as a result, it sets up a standing light wave. And this standing wave produces a laser beam, which is then extracted from this laser cavity. A microwave oven is another interesting example where there are standing microwaves, because what happens inside the microwave oven, this is what's called a cavity resonator. And the walls of the microwave oven are metal, and so the microwaves bounce off these walls and they set up standing waves, regions of high amplitude, which are the antinodes, and regions where there is no amplitude, which are called the nodes. So in the old days, the microwave ovens didn't have a rotating platform, and there would be hot spots and cold spots inside the oven due to the presence of these standing waves. Remember, standing waves don't move. They literally stand still. And so one experiment that you could do in an old microwave oven, or even a new one if you take out the rotating platform, is you can place butter along, say, a plate inside the microwave, and wherever the hot spot is, you'll find the butter melts, and in between the hot spots there are cold spots where the butter will not melt. And there's an interesting experiment you can do. You can actually measure the speed of light by measuring the wavelength of these hot and cold spots in your microwave. Okay. One of the most fascinating effects of standing waves are acoustical standing waves, which are standing sound waves. And we can see how it works here with this animation. So this picture on top, this is a right traveling sound wave. So remember what sound is. It's basically vibrations of the air molecules forming compressions, which are these dark regions where the molecules are closer together, and rarefactions in between. So you can see the compressions here are moving to the right. So this is in here we can graph the pressure versus position, and we have a right traveling wave. Well, if this sound wave bounces off the end of this tube here, then we're going to have a left traveling wave coming back the other way, and that's what's shown here. But what we actually hear, of course, is the effect of both of these waves superimposed on top of each other. And look what happens when we combine them. We get a standing sound wave. So notice these regions of nodes and antinodes, they don't change position. They just alternate high and low, as is shown down here. So this is an example of a standing sound wave. And we learned in the last part of this lecture, in part 1, that standing waves are produced whenever waves are confined to a medium, basically, that holds the waves inside. So for example, we looked at a string tied on both ends, so it was fixed, so the waves had to bounce back and forth. And remember that these waves that bounce back and forth then interfere with each other and produce standing waves. So musical instruments are based on this, whether it's a woodwind or a brass or even a string instrument, they all are based on this principle of standing waves. If we think about woodwind instruments like flutes, saxophones, clarinets, and so forth, the tubes where the sound is produced in these tubes will only allow standing waves, which remember is constructive interference, at certain frequencies or wavelengths that are related to the tube length. All other frequencies result in destructive interference, meaning no sound. So for a flute, it's open on this end where the musician blows air into it, and it's also open on the far end here where the sound leaves. So this is called technically an open tube. It's open on both ends. And these are the first 3 modes of standing waves that are produced for an open tube. And this is the mathematics here, the equations for the wavelength, 2L over M, where L is the tube length, M is the mode number, so this is M equal 1, M equal 2, M equal 3, and so forth. And then these are the frequencies that are allowed for this particular tube geometry. Again, the frequencies are based on the length of the tube there and the mode number. So in order to demonstrate this effect, let's watch a couple of videos that I made. One with creating sound in a tube using a speaker, and another shorter one where I actually whistle into a tube. Hi, I'm here again in my lab, and I want to demonstrate to you standing sound waves inside of a tube. So this is a little speaker, it's a little loudspeaker, and I've got it connected again to a signal generator back here where I can adjust the frequency by turning this knob. So you can listen to the different pitch. As I increase the frequency, you can hear the pitch of the speaker increase. And one thing you notice is that as I increase the frequency, the loudness of the sound is pretty much constant. In other words, the sound doesn't get loud or soft at particular frequencies. So what I'm going to do is, let me go down here to back down to a low frequency. I'm going to connect this speaker here to the end of this cardboard tube. And so I'm going to do this by clipping it right here, like this. And now you can see that the tube here is pretty long. It goes all the way across the desk to the other side. In fact, it's 1.87 meters in length. So it's about 6.5 feet long, almost 2 meters in length. And what I did is I did some of the calculations, like the ones shown in the lecture notes, to figure out what are the frequencies that will produce standing waves in the tube. Now remember, standing waves are called modes, and each mode represents a harmonic frequency, and you can think of it as when the frequency is in resonance with the tube. So at these, and basically that's constructive interference. That's what we have going on here. So what we predict here is that according to the calculations here, every 90 hertz, we should hear a mode or a harmonic frequency or resonance or constructive interference, whatever you want to call it. Meaning, every 90 hertz, we should hear the sound get louder. And in between those loud sounds, we should hear the sound get softer. So let's go ahead and do this experiment. So I'm going to start here we'll start here at the first loud tone, which is right here at about 410 hertz. So this is relatively loud, what you're hearing right now. Now, if I go up to 460, the sound is much softer. In fact, you can barely hear it now, right? Because this is destructive interference inside the tube. Now, remember our first mode was at 410, so if I add 90 hertz to that, we should get a loud tone at 500. So this is, again, this is 460, 470, 80, 90, and here's 500. Notice it's loud again. Let's keep going up. 540, halfway in between the louds now, is going to be soft again. You can barely hear it. From 500, we expect to hear another loud tone at 590, which is right here. So relatively loud again. Keep going up. 640, soft. Let's go up to 680, which should be the next loud. Right here, loud. Soft. And our next loud we expect at 770, right there. Soft. Here's 860, our next loud one. This one maybe not quite as obvious. And we can just keep going. We get soft, And then here's 950. This one shows up really nicely. So again, we're just going up by 90 hertz every step to get to different modes of vibration. Let's just do two more. We'll go up to, here's at 1,000, relatively soft. And our last one should be at around 1,040. Right there, loud again. So here's a little interesting demo that you can actually do at home. If you get a piece of tubing, now you can use, for example, a paper towel, an empty paper towel cardboard tube. It'll work just as well. This is a piece of plastic PVC pipe from the garage. And if you, what I'm going to do here is I'm going to whistle into the tube, and the tube is going to only allow certain frequencies or pitches to be played or heard. And so it's kind of a strange phenomena here. So for example, if I whistle without the tube, I can whistle from low to high to low, and it's a continuous spectrum of pitches or sounds. So listen to this. All right, so you heard it go up smoothly and then back down smoothly. Now watch what happens when I try to do that into the tube. This time you could hear it going up in steps. Now why is that? Well, because the tube only allows certain frequencies to resonate inside with constructive interference. These are the standing waves that we talked about in the lecture that represent different modes of vibration for the sound waves inside of this tube. So instead of allowing every different sound or pitch to be played, the tube only selects those frequencies that have to do, with the correct geometry of the sound waves fitting inside the tube. So listen again as it steps up in discrete frequencies. By the way, this is the way musical instruments work, right? Musical instruments, the geometry of the instrument actually only allows certain tones or pitches to be heard. And, with a musical instrument like a flute or clarinet or something like that, there are holes placed along the tube of the instrument, and the musician can lift up fingers and open up those holes to effectively change the length of the instrument, which will allow different pitches or different musical notes to be heard. We'll finish here with another very entertaining video demonstration that another professor has done using something called a Chladni plate. And what we've been talking about so far in this chapter is one-dimensional standing waves, and they're the simplest to envision because the wave is just moving in one direction, horizontal, for example. But there are standing waves in 2 dimensions or even 3 dimensions that are a little more complicated, and we're not going to get into the details, but we can look at some of the fascinating effects of them. So in the video, you're going to see example of 2-dimensional standing waves that are produced in a very clever way using a steel plate mounted to a speaker that plays a pitch, and by sprinkling salt crystals on top of the plate, the salt crystals will dance around and move wherever there are vibrations, but wherever there are nodes where the plate is not moving, the salt crystals will settle there because there's no vibrations. And so these white lines here show the pattern of salt crystals which mimic the pattern of the 2-dimensional standing waves. And so you'll get to see, as the frequency is increased, a lot of interesting patterns like this are produced. So enjoy that video, and then we'll...
These are known as what? Salt. I thought we did this before, you said.
Yeah.
So what did we call this?
It was in fourth year, though. So we weren't really.
So
We were just
I
looking at it like,
Okay, we'll turn it on and see what happens. And I'm on the 100th zone. I need to do two things here. I'm going to change the frequency on this button and the amplitude on this button. Except it's going to be kind of tricky, so I'm going to change the frequency. John is going to increase or decrease the amplitude as I call it out. So we turn it on. It vibrates up and down, not the biggest deal in the world, but straight away you can see where it's vibrating the most is going to be where? On the outside where the salt is. Now watch what happens when I start increasing the frequency. Feel free, once again, to show your appreciation at any stage. As soon as this starts getting boring, we stop it. The first time I saw this, I couldn't believe I actually get paid to do this sort of thing.
I don't think you're getting paid to do this.
So once again, where is it not vibrating?
Where there's no salt.
Where there's no,
Where there is salt.
where there is salt. So it's vibrating there and there. I'm also a little top heavy at this end, so I'm going to try and turn it down a little bit. You turn down the volume. Once we've got it generated, we can turn the volume back down, so we turn it up while we're changing the frequency. So up you go this time, and we go again.
It's gonna explode.
There, I go up one more level. That's what we had. What frequency am I at here? Can you tell by these two? Looking at it there, can you tell zoning on that chain?
Zoning
I'm at 1. Anybody else guess what frequency I'm at?
100 hertz.
It's 1. Any other numbers there?
What scale is it on?
Ah, you tell me.
I can't see.
Or maybe you could move.
Kilohertz.
Hertz.
Is it kilohertz?
Yeah, kilohertz. So it's 1000 hertz, right? So this guy, again, that is pretty impressive. It's going up and down 1000 times a second. Right, we go fishing again. Put more salt into it. And I try and zone in a bit more. Turn up the volume again. Okay, keep the volume constant. There you go, and back down. At this stage, I'm a bit heavy over here. I'll move that.
Is
over
that
there.
still vibrating even though we can't hear it?
That is now vibrating. Can you hear it?
Yeah.
It's vibrating 1000 times a second. Let's go again. Salt on it. I hope I'm not running out of salt.
Keep going.
Turn it up a little bit. Right, keep going.
Keep going. Volume down.
And volume down. I turn it all the way down. They're all the way down, is it?
Yeah.
Right. These are what are called Chladni plates, and patterns are known as Chladni. Patterns after a guy, I think it was from Yugoslavia or Serbia, or one of those places. He was the guy who first came up with this. And these are, you've got standing waves. So as opposed to the traditional one-dimensional standing wave on a string, here you've got some form of two-dimensional standing wave. Right? So it just looks really, really beautiful. We keep going. And we turn it back down. The next thing to notice is that even if he keeps the sound volume constant and I increase the frequency, technically if you increase the frequency and you keep the volume constant, it shouldn't seem any louder to us. Why does it seem louder to us at some frequencies than others?
Resonant frequency of the bone in your ear.
So what's going on?
In your ear.
You're more sensitive to.
Yeah, your bone actually vibrates at a specific frequency, so you're more sensitive to some frequencies than others. We go again, turn it up. Do it up all the way. I got one. Ooh, could we get a little bit more down? Keep going. Salt.
Ooh.
We're getting there. Thank you very much. We keep going.
Actually, different every time or something, isn't it?
Yep.
Wow.
That's mildly impressive.
So we've already to this
Mildly impressive.
Do we turn it off?
No, keep going.
No, keep
Keep
going.
going.
We're men here. That's awesome. Keep going.
We'll see a message. If we go far enough, we'll see a message from God.
We're gonna break on through tomorrow.
Pretty impressive.
Wow.
It can still go hard, kind of.
Whoa.
Oh.
That's really well my head.
Keep going.
Why?
Top heavy again.
Nice thing.
Okay, we're now at the, that's one, do I turn the volume all the way down? So it's 1,000, 1 kilohertz by 10, so it's 10,000 kilohertz. So it means two things. One, that's the frequency. The second thing is we can still be sensitive to 10,000 hertz. So now we're going to go all the way back. We're going to put it at the 10,000 hertz range.
You're crazy.
So you're going to do two different things. One, we will find the frequencies between 1 and 2 are actually the frequencies between what and what?
10 and 20,000.
10,000 and 20,000 hertz. And the second thing we should notice is as we approach 20,000, it just goes outside our levels of audibility. So we've got a minute left here, so we'll keep going. Here we go again.
Can you get a bigger plate and will the patterns keep going?
Yeah. I was thinking
It's
that
a
one.
joint plate.
Sorry, right there, Louise, turn the, that's good, isn't it? There we go. There's a nice one. Okay,
It's like goggles.
let's go again.
Thanks, sir.
I'm done.
Thanks, Dad. Still a tiny bit.
You know the frequency of what? Looking at it there?
It's gone there now.
Just coming up
Hey,
at 20,000
hey.
hertz. So at 20,000, we're going back down. See if I can get a pattern right there.
Please, stop.
So last one.
It's horrible. Ringing.
Can you still hear it?
Just
Yeah.
let it become.
I'm
Volume's
so
up to the
glad I'm
max.
first to go.
No, we're not really getting. Oh, we are getting a tiny bit of a
Calm
pattern.
down.
Oh, yeah, we are.
I can
No, I'm
still
gone.
just hear it.
No, I can't hear it. I do.
The patterns get smaller as you go up.
That's at about 18,000. What gets smaller?
The patterns, do they? Because the wavelength's less.
They're getting more detailed,
Yeah.
and it's going up and down more quickly. When you say it's getting smaller.
So whether it's just finer spaces that it's not vibrating.
Oh yes, I suppose that'd be right. I hadn't thought about that. That'd be right. I hadn't got that pattern before. That's very, very impressive. Let's see if we can get one more on that basis.